Gas tungsten arc welding is officially defined as a process that uses an arc between a non-consumable tungsten electrode and the workpiece. It's usually shielded by an inert gas like argon, and it does not involve the application of pressure. You're going to commonly hear it referred to in the shop as TIG, or tungsten inert gas, and you may even hear some people refer to it as heliarc because when the process was first developed, it used helium shielding gas in order to make welds. All right, if we take a look at the process diagram, this illustration shows the travel direction going from right to left across the screen. And normally we would use a push or a forehand technique, and we'd tilt that torch back about 10 to 15 degrees to point the tungsten in the direction of travel. You can see there that if we're going to add filler metal to the process, it's going to be added at about a 10 to 15 degree angle up from the base metal, and it should go directly into the weld pool because you want the weld pool to melt that filler rod. You also want to have good rhythm, and you can see the illustration shows perfectly stacked weld beads, and you can achieve that also if you have good rhythm and you add that filler rod in a nice consistent fashion. You can see the tungsten electrode has a sharp taper on the end. That helps to provide increased current density and better arc control. And the slightly gray area that's labeled as the shielding gas envelope illustrates the effective area that the shielding gas is going to cover, because the purpose of the gas is really to protect the tungsten while you're welding and also to protect the base metal while it cools from welding temperatures. TIG process fundamentals begin with the fact that it's a constant current process. And when you think about it, you're walking up to the power source, you're going to set your current or your amperage on the front panel. And you may also be able to control that remotely if you have a foot pedal or a fingertip control hooked up to the system. And your voltage is going to be determined by your arc length. Usually with TIG welding, we want to use a nice controlled arc length because it does a couple of things. It keeps the arc from spreading out too wide, and it also makes sure that the shielding gas is contained around the weld. So voltage is something that you're going to want to pay attention to, and keeping a consistent arc length is key to achieving good weld quality. Filler metal is controlled by the operator in this process because the arc really comes off the tungsten. It's not consumed into the weld pool, which means if we have two options, we're either going to use the base material and perform an autogenous weld where we're just fusing the base metal together without adding any external filler metal, or the filler rod could be added by hand, usually in cut lengths about 36 inches long, or using a mechanized device like a wire feeder. And basically adding that filler wire right into the puddle adds weld reinforcement and gives it some additional strength. Now, TIG process advantages include high quality and precision. This process is able to provide pinpoint control of the arc as it comes off the end of that very small tungsten electrode. Shielding gases provide excellent coverage and protection from oxidation, so we get very clean welds that have no oxidation on them, are very shiny and look really aesthetically pleasing. And the operator controls when and how much filler metal to add to the weld pool, so a skilled operator can make sure that that weld has a very desirable profile. The process is also highly efficient and clean, meaning there is no flux or slag, so what you pay for and what the filler metal that you use typically ends up in the puddle because there's very little stub loss at the end of the day. The process produces no sparks, no spatter, no slag, has very low fume generation, and as a result, most of what you pay for goes into the work, and you don't have to deal with a lot of the other issues that you would normally encounter with a consumable electrode process like gas metal arc or MIG welding, and of course shielded metal arc or stick welding, which tend to produce significant amount of spatter, smoke, and even slag. TIG is also very capable. It welds more metals than any other process. In fact, it can achieve high quality, even X-ray quality welds on almost every material out there that's weldable. And it's capable of welding in all positions, so it's extremely versatile. The TIG process does have some limitations, and they begin first and foremost with the fact that it's relatively slow in terms of productivity. Travel speeds are slower than with MIG welding. and you're typically going to see low deposition rate in terms of pounds or kilograms per hour. TIG is also susceptible to contamination because we're using a shielding gas. It is susceptible to wind and draft, which can blow away the shielding gas and cause you to have issues like porosity and oxidation. So it is a concern, and often it cannot be done in very windy conditions without building a shelter around the weld zone. Otherwise, it's ideal to be used indoors. Any paints, oils, rust, or oxidation should also be removed because it's going to contaminate your tungsten, it's going to contaminate your weld pool, and often result in some fume generation that's usually not very pleasant to breathe. High operator skill is usually associated with TIG welding because there's a number of things going on under the hood. The operator has to control the TIG torch, the addition of filler metal with the opposite hand, and then sometimes you may have a foot pedal or a fingertip remote just to add one more thing to your juggling act while you're trying to make a good weld. So it's really important to maintain consistent torch control, again, to maintain consistent voltage while we're welding and a consistent welding speed. You also, again, want to have that good filler metal rhythm and placement so that you're adding the filler rod to the leading edge of the puddle. And again, using a nice consistent rhythm, because every time you add filler rod to the puddle, it makes a nice ripple pattern in the weld. And the ability to remotely control welding gives the operator the ability to adjust the arc based on puddle width, which usually determines how much current they're putting in. A wider puddle usually means we're using more heat, and a narrow puddle means we're using less heat. So the operator can make that judgment call and make judgments on the fly. And that can also be a curse because it's one more thing, like I say, to have to pay attention to. And oftentimes people tend to weld like they drive a car, and they go all the way to the floor. And that's a bad thing when you're driving, and it's also a bad thing when you're TIG welding because usually you make holes in your material. TIG welding is used in a variety of markets that value its precision and versatility. And one of those, of course, is aerospace. When I think of TIG welding, I immediately think of the high quality and precision required in aerospace. And we see that used in a lot of engine components, duct work on the aircraft, and of course, throughout the life cycle of the aircraft, as most of the time it's repaired over and over again, inspected, and then put back into aircraft and put back into service. Other markets that use TIG include the pipe and pressure vessel industry because of the high quality and precision. TIG welding is able to make very clean welds with full penetration on a variety of thicknesses. And again, for applications like pharmaceutical and food processing, there's no sparks, no spatter, no slag, nothing that could become a part of our next meal, which of course is undesirable. So you see TIG get used in a variety of those markets and applications. And when I think today of the popular growth areas would be the brewery industry and the winemaking industry, which have started to pop up all over the state and all over the country. Other markets include the marine industry. Obviously, the Navy is a large user of TIG because most of its vessels are floating cities. So they've got kitchen hardware and galleys on board, if you will. They've got plumbing, heating, and cooling systems that all require some TIG welding. And then, of course, TIG welding provides the weld quality that they need when they're taking these things into extreme conditions. Other areas that we don't often think of would be the sporting industry, and the boat that's illustrated there, the pleasure boat, has a large T-top or tuna tower that is anodized aluminum that helps to get those fishing rods up and away from the boat and spread things out so they can cover more ocean territory. So very, very common to see a lot of aluminum used because it does have corrosion resistance, and it's also extremely light, which is valuable in the marine industry. Other TIG markets that you might not consider would include the medical and dental industry. You may not know it, but TIG welding is used to make hypodermic needles. It's actually a somewhat specialized process that involves a large tube mill that rolls a strip using a set of forming dies, and then TIG welding is used to form the seam before those needles or that material is drawn down into the diameter they need for a hypodermic needle. I've also worked with customers and people out there who are in the business of making medical devices that include arthroscopic surgery tools, and a lot of those are TIG welded using microscopes and very precision welding procedures. Another interesting market or aspect of the medical field that I was involved with in the past included the welding and repair of titanium castings used for artificial joints, such as this hip that's shown on the slide. Many times those are high quality titanium castings, but they still have some flaws in them. And of course, after they get done machining that down, they want everything to be smooth and flat. So if there's any gouges or voids in the casting, a lot of times TIG welding is used to repair those before they go into the final machining process, and then ultimately get sent out to a customer or an end user whose needs a joint. Following the line of micro welding, other places that you might see TIG welding get used include the repair and manufacturing of jewelry, because TIG welding is capable of joining everything, including gold, silver, platinum, palladium, and a lot of the exotic materials that are used to make jewelry. And also the picture in the middle that illustrates a microscope and some microscopic TIG welding is really in the tool and die industry, which a lot of times values the precision weld placement as we rebuild molds and dies that are used out in industry. Lasers are also involved in this market because a lot of times the precision requires even more than what TIG is capable of achieving. Other markets that you see TIG used extensively include the automotive and customizing market. Many people were building hot rods after a show called Orange County Choppers, or OCC, gave way to a new venue of reality TV and inspired a lot of people to explore their creativity. Also see a lot of folks restoring hot rods and doing different automotive restoration, where TIG welding is very popular to make custom components and to patch old parts. And then, of course, a lot of the components that you see, especially in performance automotive, would be TIG welded, like the radiator that you see off to the side that's definitely intended for high performance racing. And of course, you also see hobby enthusiasts in a wide variety of markets using TIG welding because it's a very versatile process, produces very high quality, and it's able to weld so many different materials. So everybody from off-road motorsports to sport aviation and home build aviation, right on to, like I say, auto restoration and things that you might do out in the workshop. This picture illustrates how a welder might approach a joint to start making a TIG weld. And what you see, and you should notice, is how he's holding the TIG torch allows him to place his hand underneath the torch and support it or rest it to stabilize that torch, again, to provide consistent travel speed and arc length for a consistent weld voltage. He's got the torch tilted back just a little bit to point the tungsten in the direction of travel, and you can see the filler rod in his left hand that he'll add to the puddle as things get going. Now, when you look at the PowerPoint presentation online, this will be a video that you can watch, but in this case, we're going to skip right over it. This is going to look like a slide for you, but go ahead and check that out in the PowerPoint. All right, when we start talking about the TIG welding process and we get into the nitty-gritty, it's important to begin with the weld sequence, because a lot of the terminology that we're going to use moving forward begins right here at this foundation. And if we're able to graph the weld process in terms of time as it moves along on the bottom of the graph, and current as we increase it and step up and decrease it at the end of the weld, you can see that there are some distinct phases that we're going to be talking about. And basically, when the remote control is pressed, the first thing that's going to happen is called pre-flow. And pre-flow is basically there to purge the area from atmosphere, provide a nice inert atmosphere of argon in most cases, and sometimes other gases. And then it also aids with arc starting. And usually just a little burst of gas to purge that area prior to the arc start is all that we need, unless we're working on a highly specialized application or with a material that's highly reactive like titanium. So we're going to recommend about 0.2 to 0.4 of a second. Once that time's out, the arc is going to start, and usually that's using a high frequency discharge, but it could also be a contact ignition method we'll discuss in a minute. And once the arc starts, we're going to basically jump to our initial current setting. And usually that's a lower setting that allows us to stabilize the arc before we ramp to the welding current during our initial slope time. But just note that that also could be a hot start, because some materials like aluminum require a little bit more heat to form the puddle, and then we may back down on that to our peak or our welding current. So just note that most of the time the initial current is lower and we're ramping up to a peak welding current, and but sometimes we may actually have that initial current be a little bit higher in some special applications. When we get to our peak current, you can see there that the recommendation is about 1 amp for every 1,000th of an inch thickness. So in terms of 1/8 inch material, if that is 0.125 inches, we're basically going to require about 125 amps to weld that material. And that's where I'd probably set my machine. In terms of millimeters, we basically would need about 40 amps per millimeter. And I believe 1/8 of an inch is a 3.2 millimeters. So we would probably be again in that 120 to 125 amp range. After you're done welding and you basically start to back off the remote control, and you enter what would be called the final slope phase that allows us to control the size of the weld crater. And basically it allows the weld puddle to solidify before we get to our final current, where we can add just a little bit more filler rod before the weld solidifies, and then the arc would end. And ideally we would not have a large crater at the end of the weld. Following the arc end, we would go immediately into our post-flow cycle, and we recommend about 1 second for every 10 amps for most welds. So if you were welding at about 100 amps, you need about 10 seconds of post-flow, and that helps to protect the end of the weld as it cools down to room temperature, and it helps to protect the tungsten electrode from oxidation. If your tungsten turns blue or black, you probably need a little bit more post-flow time or a higher gas flow rate to, again, protect that from oxidation. Okay, as I mentioned, we were going to talk about different ways to start the arc. And if you remember, the tungsten is a non-consumable electrode. So if it's not consumed in the arc, we usually, as a rule, would think you probably don't want to come into contact with the base metal, because it could cause cross-contamination. And that's exactly right. As a result, non-contact ignition is usually preferred for TIG welding, especially in high-end application. And this often it involves what they call high frequency, which is a high voltage that can jump a short gap. Basically, usually the diameter of the electrode, we don't want that tungsten gap to be too much longer than the diameter of the electrode. And the high frequency would basically jump from the electrode to the work, the current would follow it, and we would have our arc started without actually coming into contact with the material. This does generate some electrical noise, and high frequency has been known to interfere with computers and nearby electrical equipment. So sometimes special grounding is required, and if that's not possible and you're still noticing some interference, you may want to change to a contact ignition. Contact ignition is not allowed in some critical applications, but for the most part, done properly, it can be done with success without major contamination. Now, a scratch start is basically turning the output of the machine on and scratching the tungsten on the work to get the arc started. And that usually involves, like I say, dragging the tungsten on the work there. And Sometimes that tungsten can grab the work and actually weld itself to the work and cause some cross-contamination. So lift arc and touch start are two different features been developed by power source manufacturers that basically use a sensing voltage before they turn on the output. And as you make contact with the work, the output energizes, and when you break contact, you have a nice arc start without welding the tungsten to the work. So sometimes you may see that used, and many times that's preferred out in the field when we don't have high frequency, or when you can't use a remote control to engage the high frequency. In many cases, then scratch start or lift arc is preferred. All right, high frequency arc starting application. If you look at this image, which again will be a video in the online presentation, you can see how close the tungsten electrode is to the work and where the operator is basically going to engage the foot pedal, start the high frequency, it'll jump that gap, the arc will follow, and he can begin to add filler metal to the molten puddle as he travels on the screen from left to right, pushing the puddle in the direction of travel. All right, this image, which is a video that would also show lift arc starting, and when you check this out in the online presentation, you'll see the tungsten coming down, touching the work, and then as the tungsten is lifted away, the arc engages. All right, so if we talk about TIG welding, it's also important to discuss the effects of welding current and polarity on this process. Being that it's a non-consumable electrode, it behaves a little bit differently than shielded metal arc welding or stick welding, and definitely differently than flux core or MIG welding. First of all, direct current electrode negative allows the tungsten to stay nice and sharp because it directs most of the heat into the work, gives us really good penetration, good tungsten capacity. And if we switch to polarity and we look at DC electrode positive, it does the opposite. It directs most of the heat up onto the tungsten, causing it to ball back severely, erode, and be consumed by the arc, which is not ideal. It gives shallow, wide penetration and very poor electrode capacity. As you can see, a 1/4 inch tungsten will only tolerate about 120 amps. So as a result, DC electrode positive is not very desirable because it consumes your non-consumable tungsten electrode. And as a result, we would prefer to use DC electrode negative because it produces such good results on most materials. In terms of AC, which is another option to use, it would basically provide electrode negative benefits and electrode positive benefits without severely balling the tungsten, giving us a little bit of extra electrode capacity. But because it contains electrode positive, it's still going to give us a little bit of that undesirable balling action and help to erode the tungsten. All right, so DC electrode negative, again, it directs heat into the work, minimizing tungsten erosion, keeps that sharp tip nice and consistent all the way through the weld, and it's usually ideal for most metals. And we would see this used for carbon steel, stainless steel, copper, nickel, titanium, and most of the commonly used materials. However, DC electrode negative does have one issue. It does not handle the high melting surface oxides found on aluminum and magnesium very well. DC electrode negative provides no cleaning action, and it can be used with extreme care with 100% helium gas and thorough cleaning of the surface, usually on thick sections, but it's not usually recommended for welding aluminum. The better solution is to use alternating current, which, as we discussed before, contains a little bit of electrode positive, which can be used to control the amount of arc cleaning that helps to remove that high melting surface oxide so that we can form a puddle on aluminum. All right, now alternating current doesn't come without its issues either. First of all, a sine wave, which is depicted over onto the right-hand side of the screen, shows what's called the zero crossover area, which is when the welding current has to change polarity, and it actually has to go to zero current because current can't flow two ways in a circuit. So the current actually goes out for a moment before it reignites in the opposite direction, and that can cause major arc stability issues with AC. And it wasn't until the 1950s that they figured out that firing the high frequency used to start the arc would help the arc to reignite as the current changed polarity and provide what is known as arc stabilization. So many of the older power sources require continuous high frequency when welding aluminum for that reason. Another thing that we noticed about welding with early AC was you got a balanced wave, which meant out of one cycle, half of it was positive and half of it was negative, which sometimes during that positive cycle, it could consume your tungsten more than you would want it to. So we had to use larger diameter tungsten than you normally would in a comparable DC application. That would help to resist some of the erosion that's going to be caused by the electrode positive as a consequence of using the process. All right. AC wave output controls were introduced in the 1970s, beginning with square wave technology. And that square wave technology sped up the time that we change polarity from positive to negative using internal electronic controls called silicon-controlled rectifiers. That helped to stabilize the AC output and provide much better welding characteristics for welding aluminum. Another AC output control that's very useful is AC balance, which was initially introduced in the 1970s. And this control sets the ratio of electrode negative to electrode positive in an AC cycle. And increasing the amount of electrode negative, which decreases the amount of electrode positive, helps to control the cleaning action. And it also helps to reduce tungsten erosion while directing most of the heat into the work so that we can get good travel speeds, excellent puddle wetting action, and still have enough cleaning action to provide a good weld. And one of the things that you're going to look for when you're making a weld is usually we start out around 70 or 75% electrode negative. If the weld puddle has oxides that look like pepper flakes floating on the surface, then you're going to want to turn that balance down a little bit because that will increase the amount of electrode positive and increase the amount of cleaning, which is somewhat backwards that you turn the control down to get more cleaning. This video illustrates the cleaning action generated on aluminum during a normal TIG welding arc. And this video illustrates the AC balance when it's set too high. And during the weld, you'll notice that there are pepper flakes on the puddle that are indicative of too much electrode negative and not enough electrode positive. All right, another AC control that's extremely useful and helps to improve arc stability and directional control is AC frequency, which controls the amount of AC cycles per second. So traditional machines were fixed at the input frequency of 60 hertz in North America, 50 hertz in other countries around the world. And modern day equipment is able to change the output frequency to achieve different arc characteristics. And very commonly, we would see a 60 hertz arc producing relatively wide a wide arc with the susceptibility of wandering and the arc dancing around the end of the tungsten. When we increase that to 120 cycles per second, the arc becomes much more focused. All right, this video illustrates the arc wander that occurs in a T-joint when welding with a 60 hertz arc. This video illustrates the focused arc that results with an AC frequency of 120 hertz or even higher. Another AC wave control that's somewhat advanced and not available on all equipment is independent amperage control. This advanced control feature allows you to set the electrode positive and the electrode current individually. So you may only have 100 amps positive while you have 300 amps negative. This emphasizes AC balance control by only giving you enough time and current to clean the material and not any extra to ball the tungsten. So it helps you to keep you an even sharper point on the tungsten electrode, and it further decreases tungsten erosion. But like I say, it's not always essential for every application, and usually it's only available on the most advanced equipment. Another advanced option that is out there includes AC wave shape selection, and the different waveforms that you see off on the right-hand side of the screen include soft square wave, true or advanced square wave, advanced sine wave, and then what we call sawtooth or triangular waveform. And basically what you see is the sharper the curves, the more aggressive the arc is, the noisier it is, and the softer, the more rounded the curves are, the softer the arc and the softer the noise is when you're welding. Now, while most people aren't going to notice a major change between any of these waveforms, there are subtle differences that include the puddle wetting action, weld penetration, and ultimately directional control in critical applications. But most people are going to find that a soft square wave works the best, and that's usually the default for most of the modern equipment, where we get good transition through the zero crossover area, and the arc provides nice wetting action and good puddle control. All right, a gas tungsten arc welding system is illustrated in the picture below, and the mandatory equipment that we have to have includes a power source, the shielding gas and regulator, our TIG torch, and our work clamp. A coolant system, if we're using a water-cooled torch, and a remote control would be benefits to improving weld control and weld quality, but they are not required to actually perform a TIG weld. All right, let's talk about TIG power sources. As we discussed earlier, they are constant current machines. When you walk up to the front of the machine, you're going to set the current, and then you might use a remote control to control your amperage during the weld. Now, this could be any constant current machine, including an engine drive, a stick welding machine, or any other machine that produces constant current output, as long as you have the right hardware to go along with it, which would include your gas valves, torches, and things like that. Often TIG equipment is dedicated, and it provides specialized controls for TIG welding. For example, many of the machines illustrated below in the pictures provide internal gas valves, plug-ins to plug in water circulating devices. They provide high-frequency arc starters that aren't standard in most of your other equipment. So they're really dedicated for TIG welding in many cases. Now let's talk TIG torches. They do three main things. They hold the tungsten electrode, they direct shielding gas around the weld, and they provide a handle for the operator to hold onto. There's two main types of torches. Air or gas-cooled torches tend to be larger in size to dissipate the heat, but they're a more simplified system because they don't require any cooling devices. Water or liquid-cooled torches are usually smaller designs because water and liquid cools more efficiently than air, but this does add complexity to the welding system with the requirement of a cooling system for the torches. Torches are rated based on their current and duty cycle. There are a number of different sizes available, and they are available in the standard lengths of 12 and 25 foot lengths. These images illustrate a couple of specialty torches that are available for TIG welding that include a locking knuckle for positioning the head of the TIG torch and locking it into place. Other designs may include flex heads, torches with valves, and other configurations for specialized applications. These images show a couple of other options that you might run into with TIG torches. As you can see, the picture on the left shows a wide variety of TIG torches, sizes, and configurations. And the TIG torches on the right are actually designed for automated use. So they would be used on a robot or some type of fixed automation that would grab onto the TIG torch around the barrel. Torch consumables include a nozzle to direct shielding gas around the weld, a collet and collet body to apply pressure and hold the tungsten into position, a torch body with torch handle and torch neck, and a back cap, which applies pressure to the back of the collet. As you can see down in the lower left-hand corner, you can also change out the collet body for a gas lens and use a dedicated nozzle that provides extra shielding properties and allows for longer tungsten stick out when you're making a weld. As you can see here in the image, no gas lens is used in the image on the left, which is depicting a very turbulent gas flow. And if we take a look at the image on the right that's using a gas lens, you can see that the gas flow is very columnar and streamlined without a lot of turbulence, indicating that the gas coverage is improved. And what this allows you to do is stick the tungsten electrode out much further than you normally would be able to and still achieve excellent shielding. Torch coolant systems include probably the most common type, which is a coolant recirculator. These are closed loop systems. They may actually be a manifold or an individual system, but they basically circulate some type of a coolant through a heat exchanger that does not involve refrigerating anything. Refrigerant coolers are typically reserved for high-end applications like lasers and electron beam welders, whereas we can get away with just circulating coolant through a heat exchanger and passing ambient air over it for TIG welding. Coolants can vary. They range from high quality tap water, which can freeze in some applications, so that's a concern. When that is a concern, you should use a low conductivity antifreeze from the manufacturer of the welding equipment. Do not use automotive antifreeze because that contains minerals that can conduct high frequency away from the arc, which can cause arc issues when you're welding. Some special systems even use alcohol, and that actually provides excellent cooling, but you have to have the right cooler and the right hardware designed to use that as a cooling system. Remote controls used for TIG welding range from using none and just going with a scratch start and welding at the preset panel current, which doesn't give you a lot of control, to most commonly used foot control, which is excellent for bench and fabrication jobs where you don't have to move around a whole lot and you're usually working on the ground. In case you're doing field construction or working up off the ground where you can't use a foot pedal very easily, they do make fingertip controls that mount to the back of the torch that include sliders and potentiometers to give you remote output on off, and also to give you remote current control to manage your weld under the hood in real time on the fly. They also make hand control boxes, which are really designed for stick welding and or scratch start TIG. And what it allows you to do when you're working hundreds of feet away from your machine, you can change the preset output, go to weld. When you get done with the weld, you can change that preset output again, but they are not designed to typically change the output of the machine while welding. Hence, that's why they look like they would clip onto your belt and not be very accessible when you're welding. Now let's talk tungsten electrodes. There's many flavors available for TIG welding, and they include a pure tungsten electrode and several that contain different metal oxides to improve tungsten properties. Each type is color-coded so you can differentiate between them when you're using them, and each electrode has different properties for gas tungsten arc welding. If we take a look below, you'll see that green indicates a pure tungsten electrode, brown and white are zirconiated tungsten, red is thoriated, which is also radioactive, gold and blue are lanthanated, gray is ceriated, and blue and purple, light blue and purple, are trimix tungstens, which are technically not designated as specific classes. All right, if we take a look at the following tungsten electrode chart, it lets us know that pure and zirconium work best in AC because they tend to form a ball when welding, which is typically a consequence of using AC that has a little bit of electrode positive in it. Pure tungsten forms a large ball, so it's best with older power sources. Zirconium, again, can only be used with AC, and it's actually an X-ray quality substitute for pure tungsten. Thorium tungsten is the red tungsten, and that's really good for DC electrode negative primarily. It will work in AC, but it produces undesirable nodules on the end of the tungsten, and it doesn't ball very well. So many times we have an erratic arc and poor arc starts when we use thorium. Cerium and lanthanum are your best all-around options. They work good in AC or DC. They do resist balling a fair amount, so many times in AC you can weld with a slight taper to your tungsten, giving you better arc control. And the trimix tungstens are substitute for any of the above, and initially they were developed for very long cycle times, so if you're ever welding in an automated application with a cycle time of 15 minutes or more, trimix tungsten might be the way to go, but otherwise they perform equal to or comparable to thorium, cerium, and lanthanum. I just find that cerium and lanthanum are more readily available, and usually I don't have to pay for somebody's proprietary trimix, so I tend to go with those two tungsten choices. All right, tungsten electrodes are mostly 7 inches in length, although some custom lengths are available. They're also available in diameters from about 20 thousandths of an inch to about 1/4 of an inch, or 1 millimeter to 6.4 millimeters. And each electrode diameter is rated according to the maximum amperage and the welding polarity that's being used. Because as you can imagine, when we're using alternating current or electrode positive, we're going to have much lower amperage capacity than if we're using DC electrode negative. This chart here that I've created basically takes the best of both worlds. We have the lowest performance and the highest performance, so we have a total range, and you'll see that pure tungsten has slightly lower operating range, and again, it tends to form a ball during welding no matter what you do. So usually we would shift over to an oxide-bearing tungsten whenever possible. And again, cerium and lanthanum are my two favorites. Electrode preparation is key. It's something that we don't want to overlook. And first of all, you should know that a sharp point is ideal for TIG welding because it increases current density, provides excellent arc starting, good arc focus and control. And as a result, we should use a dedicated high grit or diamond wheel of at least 300 grit in order to sharpen most tungsten electrodes. You should also grind in a longitudinal direction along the length of the tungsten from the tip down, not around the tungsten, which could produce a spiral grinding pattern and cause your arc to wander off to the side and arc where you don't want it to. Always expect some electrode erosion even when welding in DC electrode negative, so you periodically should sharpen your tungsten to keep it fresh. Some balling may occur if you're welding in AC, and blunting the tip at the end may limit or slow erosion, so it actually increases the surface area, which can handle a little bit more heat before it erodes or balls back. Now let's talk shielding gases for TIG welding. Argon is the most common shielding gas used. It's heavier than air, so it provides a good blanket of shielding that resists cross drafts. It's got low ionization potential, which means at a low voltage, it starts to conduct electricity, which makes arc starting very consistent and very easy. It also provides good cleaning action on aluminum and is readily extracted from the atmosphere using the air separation process. And it's able to weld all metals with the right power source. Helium, on the other hand, is also an inert gas, but it's lighter than air and it floats away. And as a result, you have to use a lot more helium and higher flow rates in order to get less shielding. It's got a higher ionization potential than argon, which means arc starting is more difficult because it requires a higher voltage before helium wants to conduct electricity. It also provides no arc cleaning action in AC, and helium is extremely scarce on planet Earth. I don't know if you realized it, but helium is actually mined from the Earth because there's not enough of it in the atmosphere to extract using the air separation process that we use to obtain argon, oxygen, and other materials. So as a result, helium is extremely expensive, and once you use it, it's basically lost and gone forever because it floats out into the stratosphere where we have a very difficult time recapturing it. Oftentimes, in order to get some of the benefits of helium, which does provide more heat input and puddle fluidity, we would blend that with argon to achieve the benefits of both worlds. Again, other shielding gas options for TIG welding include specialized mixes with argon for advanced applications. It's good to note that these custom blends usually come at a higher cost than pure argon, and they're typically not required unless we're doing an advanced application or trying to weld super thick material and we're limited on the output of the machine. But argon and helium can be blended together to provide the benefits of argon shielding with the increased heat input and puddle fluidity of helium. Usually we see 25%, 50%, and sometimes 70%, 75% helium used in the industry, and each of those would probably be standard options you could order from a gas supplier. Argon and hydrogen mixtures are also commonly used, but they're reserved for high-end stainless steel applications and usually use about 2 to 5% hydrogen and argon, which is a common mix because hydrogen is a reducing agent and helps to actually clean the material and gives you really good as-welded properties. And in applications like high-purity stainless steel welding for food-grade and pharmaceutical applications, that hydrogen does two things: improves weld cleanliness, and it also increases travel speed for higher productivity. Now, in order to use your shielding gas, you got to have the right hardware, and that usually begins with a high-pressure cylinder. These cylinders, like the one depicted, can be pressurized up to 2,650 psi. They are available in various sizes or heights, and the capacity is measured in cubic feet that would be contained in the cylinder. You also need a gas regulator or flow meter, and the idea of the regulator is to convert that high storage pressure to a lower working pressure, and then basically to establish a flow rate in cubic feet per hour that is required to shield the weld. And 15 to 30 cubic feet per hour tend to be very common for indoor TIG, and 25 to 50 cubic feet per hour tend to be more common for welding in drafts or welding outdoors. You also need gas hoses and connections that should be high quality rubber that are dedicated for inert gas handling, or vinyl can also be used. Fittings are usually special brass connections that you can see up there, and they don't typically require a lot of Teflon tape. You basically have a brass on brass connection. Other options for shielding gas include bulk systems, but those are usually reserved for high-end industrial applications that go through a lot of gas. Most everybody else is running off of a cylinder, much like the one that you see here in the picture. Okay, that was a lot of information, but let's summarize. TIG welding is a highly capable process that can weld more metals and metal alloys than any other arc welding process. It provides excellent weld quality and allows for accuracy and precision placement of the weld bead. DC electrode negative is the primary polarity used to weld most metals, except for aluminum and magnesium, and then we're going to use alternating current. Remember that DC electrode positive is seldom used because it consumes the tungsten so rapidly, and usually that's your indication that you have things hooked up backwards. So if you're TIG welding and you notice your tungsten vaporizes when you strike an arc, make sure you have your shielding gas turned on, but flip your electrode, make sure you're running electrode negative. Remember that quality TIG welding results require care. You have to have good shielding gas coverage. You have to properly prepare your tungsten and have excellent grinding techniques. You have to remove surface contaminants to avoid issues like porosity. And you have to have good rhythm that combines your welding travel speed and your filler metal additions so that you get consistent results. Like I say, we talked about a lot of information in this discussion, but you really have all the information you need now to get started TIG welding and go from there.